Now that we've talked about how energy is stored, both in potential and kinetic forms, now we're ready to talk about the total conservation of energy. And to start with, all the energy is in one of two forms. It's either in kinetic energy or it's in potential energy. So to start with, the total energy is kinetic energy plus potential energy. Now we know from the famous saying, energy can be neither created nor destroyed, that the energy at the end has to be the same. Now technically that's saying wrong. It was written before we discovered that E equals mc squared. So you can create and destroy energy, either by splitting or fusing nuclei, or by moving things to relativistic velocities. But you're not going to have to do this for this video, so we can just ignore that. So what does this mean? The energy at the beginning has to equal the energy at the end. So the energy at the end is the new kinetic energy, plus the new potential energy, but something else. What about other things that are interfering? For instance, friction, or someone helps push something to bring it up to speed. We need to include work. So the kinetic energy initial plus the potential energy, also initial, equals final kinetic energy plus final potential energy plus work. Now it's important to remember, work can either be positive or negative. If it's opposite the direction of motion, it's negative, it's slowing the thing down. Or if it's in the direction of motion, it's positive and speeding the thing up. So let's do some examples, because this is the easiest way to cover this. Let's imagine a ball at the top of a hill. And the hill's 40 meters high, and the ball's 1 kilogram. How fast is the ball going to be going when it comes out the bottom of the hill? So let's try to do this together. The kinetic energy at the top is 0. The potential energy is mass, gravity, height. 10 times 40 times 1. So that's going to equal 400. What's the kinetic energy? Well, kinetic energy is 1/2 mv squared. At the bottom, it's reached a resting height. It has no farther down to go, so that's 0. And there's no external forces, so that's also 0. So now let's do the math. Mass is just 1, so we can cancel that out. Multiplying by 2, 800 equals velocity squared. So velocity equals the square root of 800, which is going to come out to be approximately 28 meters per second. So it's moving at a pretty good clip once it reaches the bottom of the ramp. Now let's do this in reverse. Instead of going down the ramp, now we're going to say a bowler is trying to bowl it up the ramp. So he picks a 2 kilogram ball, nice and light, and he bowls it going up the ramp at 10 meters per second. How far up the ramp can it go? Assume the ramp's tall enough that it'll never go off the back. So let's try this again. Potential energy at the beginning is 0. It's at the bottom. Kinetic energy. This time we do have a kinetic energy at the bottom. That's 1/2 mass of 2 kilograms. Velocity squared, that's 10 squared or 100. And that's going to equal kinetic energy at the top, which is 0, plus potential energy, which is mgh, plus work, of which there's none, so also 0. This multiplies out, the 2's cancel, leaving 100. So 100 equals mgh, mass is 2, times we'll say gravity's 10, it's not quite accurate, but close enough, times height. We divide both sides by 20, and height equals 5 meters. So this solves out really easily. But the thing is, so far, we've been ignoring work. We've been saying there's no work being done. But let's take a slightly different example. Let's go back to a 20-meter ramp, and there's a 1 kilogram ball rolling down the ramp. But this time, there's some frictional force on the ramp, and the frictional force is always 10 newtons opposite the direction of motion. When the ball comes off the ramp, it's only going 10 meters per second, slower than it should have been. Try to figure out how long the ramp is. Well, how do we do that? Let's look at our equation again. This time, we have to take work into account. So first let's figure out, is work positive or negative? Well, the object's moving down the hill, but the force is up the hill. So the force and the direction are opposites, so it's going to be a negative work. So potential energy to start, 20 meters times 1 kilogram times 10 meters per second squared, plus the kinetic energy, which there's none, it's stationary to start with. That's going to equal 200 joules of energy. So that has to equal the total energy and total work at the end. So let's see what we've got. 200 equals potential energy. Now we're at the bottom of the hill, so no potential energy. Plus kinetic energy. 1 half mv squared plus work. 1 half mv squared is 1 half times mass of 1 times velocity of 10. That's me 50 joules. So let's subtract that out. That's 150 joules equals work. Now work equals force times distance. We know force is 10, so let's divide through by 10. 15 joules per newton equals distance. And joules per newton, very conveniently, happens to be 15 meters. So 150 joules of the energy that was stored at the top of the hill, instead of turning into velocity at the bottom, got burned up in friction instead. So energy was absorbed in the work, and as a result, it only went 10 meters per second, and that's because it slid with a force of 10 newtons across a 15-meter ramp. So this is the kind of problem you should expect to see from this, and you should expect to see problems where you have to solve each term individually. But once you turn in all the terms you know, then whatever's left over, you should be able to solve for.